Good morning or good afternoon. Today we are going to look at partially miscible systems in the solid state. My name is Professor Orata. These are thermodynamic lectures. Now, we have talked about simple eutectic diagrams, where we have had, for example, A and B, and we have more fraction of B increasing that direction, more fraction of A increasing that direction. Then we have temperature, we call T, and we ended up with the freezing curves. When you have freezing curves, when we have freezing curves for A and B, they intersect at what we call the eutectic point. Intersecting at the eutectic point. Yes. This corresponds to the eutectic mixture plus the eutectic temperature. That is the melting point of pure B, melting point of pure A, and of course that is liquid. So in this compartment we by now know is B plus L. Here we have A plus liquid, and here we have A plus B. That's a simple eutectic diagram. And so these are the freezing curves, and they intersect at this particular point. And we have already seen that if you take a state point, which we call M1, and we lower the temperature, when we reach this point, M2, where it intersects the freezing curve at that particular point, we'll have the first primary crystals of B being formed. And of course, as you continue cooling, then we have more of B being formed, and we know that from Lever rule, or the Lever principle, we can relate the segments there to the number of moles. So we say that segment X1 represents number of moles of liquid, and segment X2 represents number of moles of B in the Lever rule. That is N of liquid, or N of B, is given by the segments of B is given as X2 rather than X1. That's Lever principle, or Lever's rule. And then, of course, when we reach this particular point, so let's call that M1 prime, when we reach this M1 double prime at this point, we have three phases coexisting in equilibrium. We have A coexisting with the eutectic mixture, and we also have B. So there are three phases coexisting in equilibrium, and if we use the phase rule under constant pressure, it is C minus P plus 1. Remember we said when you have pressure constant, it is now 1 because it is normally, the 2 normally is for temperature and pressure. So if you keep pressure constant, you are left with one variable there. If you keep both temperature and pressure constant, then you have to remove that, so F will be C minus P. So at this point where we have the three phases coexisting in equilibrium, we are going to have F is equals to the 2 component minus 3 plus 1, and that will be 0. So the system is invariant. System is invariant at that particular point. And then of course, now as you continue along this isopleth, remember, is a line of constant composition. It's a line of constant composition. Constant composition. So the isopleth, that is this line, M1, M1 prime, M1 prime, double prime, M2, double prime, M1 double, triple prime. That's an isopleth, a line of constant composition. Now, when you develop the eutectic diagram of alloys, for example, that's a mixture of metals. That's alloys, for example. And you know some of the most common alloys, which you know is where we have another alloy involving cobalt and chromium. This is cobalt. This is chromium. You can have gold and platinum. You have gold and platinum. You can have iron and carbon. And this is the basis of steel. This is a very important material, and so forth. So these are alloys, metal alloys, these are alloys. So suppose you are looking at a eutectic system for alloys. Let us take just a hypothetical case. Let us say you have A and B for alloys. Now, unlike what we had here, when you are developing the freezing curve, we are not going to have the metal pop out. For example, if you have gold and platinum, if you have gold and platinum. If you have gold and platinum, that is gold, that is platinum. You are not expecting that as you lower the temperature, gold will separate out or platinum will separate out. No, we will get solid solutions. And just think of it in a simple way. What is a solution? When you take sodium chloride and you put it in water, you form a solution. And when you form that solution, you can't quite point and say, now this is sodium, this is chloride, this is sodium, this is chloride. No, we know there is sodium chloride in that particular solution. They are there. If you add in another component, another system in that particular system, another chemical substance, they will all be which can also dissolve and be in the solution, and you have a homogeneous system. All these molecules, all these atoms and ions will all be there together in that cocktail of these atoms. In the same way, when, for example, you have gold and you have platinum, you fuse them. In other words, you melt them, they will form a solution where you have the gold atoms and you have the platinum atoms. Let's just figuratively say that we have gold, platinum, gold, platinum, gold, platinum. Let's just say one is plus, plus, one is equal, plus, equal, plus, equal, plus, equal, plus. That's to distinguish them. They will all mix up. So we have a solid solution we'll have a solid solution in that matrix there. So we have gold, platinum, gold, platinum. They are all mixed up. But you're not going to have gold separate out, you're going to have platinum separate out. So what does that mean? We form solid solutions. We form solid solutions. Where we say, let's just say that is gold, and let's just say that is platinum. They form solid solutions. Now, what kind of profile will you expect? The kind of profile which you expect these alloys is very simple. We can represent it theoretically. Let's just represent it theoretically in the sense that we have, let's say we have gold and we have platinum. Of course, small fractions, gold, a fraction of platinum. This is 100% platinum axis, that's 100% gold axis. And so what we are going to get is not the conventional detective diagram which you get. We will have liquid here, we will have the solid solution here, we'll have the liquid there and the solid solution there, liquid plus the solid solution at that particular point. Now, point number one. Definitely we know that when we fuse gold and platinum, the fusion depends on their melting points. So the one with the lowest melting point will be more in the solution. And so this is this liquid curve. It's a liquid curve. And this is a solid curve. So the one with the lowest melting point will be more in the liquid. So in this particular case, that's the melting point of gold, and that's the melting point of platinum. So we expect more of gold in that solution. And so, what about in terms of the state points? So if you take an hypothetical state point, let's call that M1, that's state point M1. Now we can tell the relative amounts of these quantities in that mixture by just drawing a tie line and dropping it. This particular point. This will give us percentage of gold, and this will give us percentage of platinum. And here we have liquid and the solid solution existing in equilibrium, and here we have the solid solution. And at the state point, you just draw the tie line, and it will give us the relative amount in that particular state point. So this liquid has that composition there. So whatever percentage of gold, of course, is out of 100%, the other balance will be that of platinum. In the solid curve, the solid solution will have that composition, will have platinum, and of course the balance will be that of gold. Now, it doesn't always follow that's the pattern. So if you look at, for example, a mixture, an alloy of chromium and cobalt. If you look at an alloy of chromium and cobalt, chromium system, then you will get a system which looks strangely. That is, we have cobalt and we have chromium. We have a system which is characterized by a minima. So we have system liquid. So here we have, let's call this A. Let's not use specifically the name. Let's just say it's two alloys. You can have A plus B. Let's not be specific because these are basically applicable to all systems, but can be a chromium, cobalt chromium system, or any other alloy. There are those which you have minimums, and there are those which you have a profile like the gold platinum which you have there. So here what we have L and A, that's the liquid, and the solid solution. Solid solution here. And here we have again L plus solid solution there. We have L plus solid solution there. And like I've said, the solution, solid solution, has both A and B in that solid matrix. Solid matrix. And so if this percentage, let's say that this corresponds to, it's about 50 in the middle, so let's say 51, 50, let's say 49%. Let's say that's 49%. Then it means that you are not going to get, for you to get pure B, that pure B could be cobalt, or could be chromium, depending on which one is in the axis. There we have cobalt, there we have chromium. Then it means that for you to get pure B, you have to operate with mixtures which have above 49% of B. You must operate with mixtures with B percentage greater than 49%. Otherwise, you won't get that. Because remember, if you have that state point there, then you're going to have solid carb, solid composition, solid solution composition, and the liquid solution composition at that point, and it will tell you what, so you can continue in that direction until you have reasonably, most of it is approaching your pure B. Most of it's approaching your pure B. At the point where now you're completing the pure B. So if you are operating below 49%, you cannot get pure B. In this particular case, if you say this is cobalt, that is chromium, then you are saying that when you are operating below 49%, you cannot get pure chromium. You cannot get pure chromium. And of course, the same will be applicable to cobalt, but now in the line of this interpretation based on this particular curve. So we look and see that indeed all these quantities differ significantly depending on what you are dealing with. So that in general, if you have different phases, for example, we can have let's say we have as I said, we have alpha, solid solution beta, we have liquid. So here we are going to have beta plus liquid. We are going to have alpha plus liquid. Of course, that's the temperature. And that is, here is alpha plus beta, whatever the components are. And again, when we are dealing with this, just like we have already seen, we can get the behavior along an isoplot. So if you have B, when you use B prime, we are crystallizing out solid solution alpha on the liquid. The amounts continue, and when you reach this particular point here, we have the three phases coexisting in equilibrium, that mixture A and B. So the system is invariant. Then when you look here, you are pulling the alpha and beta. Alpha and beta. So we are pulling. So it's very, very straightforward in terms of interpretations. But the key point there is that with the solid solutions, you don't, when you are doing your freezing curves, you will not have the solid come out as that if you have an alloy, so that one component freezes out, comes out as another does. No, it will be a solid solution, which means that you have an homogeneous mixture of these atoms in the solid structure. So solid solution is the key word there which we need to know. Solid solution is an homogeneous solution of those atoms in the solid structure. And the interpretation is basically all those of simple elliptic diagrams which we have talked about in other lectures. So make sure that you try and follow those other lectures where we have talked about elliptic diagrams for compounds, for incongruent melting systems, and for simple elliptic systems.